All right, the part we're going to start with, we're going to do mechanisms today. You basically have 2 lessons before your test, okay? Thursday, but since I'm not going to be in here Thursday, we're not going to count that as a lesson day. So I have to teach the Monday you come back from spring break. I'd like the test to be on Wednesday. It'll be on Wednesday or Friday of that week for sure, okay? I'm going to teach mechanisms today, so we're going to skip the collision theory and the activation energy. So we're kind of skipping to the end of the chapter. This is the harder one to get, I think. The other stuff is just straight math. So conceptually, this one's a little harder. It's not hard, but it's a little harder than the other one. So I'm going to teach this one earlier. Then you got spring break, right, that you can study or figure out stuff. Well, or forget it all, but anyway. All right, so where'd it go? You got it? Okay. All right, mechanisms you have seen before when you did Hess's law. You know how you had an overall reaction, Jack? You had an overall reaction, and then you had, yeah, it's the last page of your handouts. And then you had steps, right? And we added up the delta H's. Okay. That's what a mechanism is. So it looks basically like that, right? This would be step 1. This would be step 2. Okay? All right. And then it would add up to an overall reaction. All right, so first let's define a few things before we get to looking at it. You have to know that the slow step is the rate determining step. They will tell you which one's slow and which one's fast. Rate determining, I can't spell at all. All right, the slow step is the rate determining step. That makes sense, right? If you're pouring stuff through different funnels, the one with the skinniest spout, right, is going to be the rate determining funnel, right? If you're pouring sand in the sandbox, right, through different sized funnels, the smallest funnel is going to be your rate determining. The sand can't go through any faster than it can get through that slow funnel, right? So that's how this works. So we're going to write rate laws based on the slow step. Okay. The other nice thing about mechanisms is that each step in a mechanism is an elementary reaction. All right, what does that mean for you? It means that you can write the rate law based on the stoichiometry, based on the coefficients. So for an elementary reaction, and they either have to tell you it's elementary or happens in one step, or you have to see it as steps of a mechanism, you can write the rate law based on coefficients. The problem with this is once I show this to you, you now go back and try to do everything this way, okay? So if you're still given concentration versus time data, you got to graph it. If you're given concentrations and initial rates, you got to look at the chart. Do not do this unless you're told it's an elementary step or unless you're writing it for steps in a mechanism. All right, so what do I mean by it's based on the stoichiometry? If you had like 2a plus 3b makes, who knows, C plus D, who cares? All right, so we have some reaction. The rate law for this, if it's an elementary step, then the rate law is simply, the orders of the rate law are simply the coefficients of the balanced equation. Right. So it's kind of, yeah, it's like Q, yeah. So that 2 came from right there. And that 3 came from right there. Okay? All right, is this scenario likely to happen? Probably not. In the collision theory part, which is what we kind of skipped, but I'll allude to, they all have to collide, right? You've already realized that. In this case, how many molecules would have to collide in my little made-up example? 5. What are the chances 5 molecules are going to collide at the exact time with the right energy, with the right orientation? Yeah, very small. So this is probably not a likely scenario. When they talk about molecularity, I don't know what you would call 5. Of course, I had to pick something with 5. But it's either unimolecular, bimolecular, trimolecular, right? Those are kind of meaning 1, 2, 3. Oh, and you'll see this on your Mastering Chem tonight. So if it was 2A plus B, how many things have to hit? 3. So it's trimolecular. Okay, there's 3 molecules that have to hit. All right, when we look at mechanisms, let's flip over to this example. What? Yeah, what's the molecularity?
Yeah, but when it says that 3 for the rate, it's
Ter is not 4? Tetra 4?
I tried try and it said for 3 it's
TER?
TER. Yeah, TER.
Oh, it is molecular. It is. Oh, messed you up. It is ter. What's 4? I don't even know 4 off the top of my head. You're going to fail because I messed up? Okay. I'm sorry.
You should get bonus points.
Yeah, termolecular, bimolecular. And really, things aren't going to be more than termolecular, right? And they're not going to be more than 3 because then the likelihood gets further and further away. So it's very unlikely that you're going to see anything past that.
Because I find that out, can I get like
Hold
an
on.
exemption on that quiz?
Oh, and that give you an extra point? You have to
An
send me.
extra, like, 20
No, about 20, but
I'll still fail.
a couple of points maybe. Just send me an email or write you a note somewhere. Write me a note somewhere. All right, so the decomposition of nitrous oxide is believed to occur by this 2-step mechanism. So this is step 1, this is step 2. Notice they told us this is the slow step, this is the fast step. All right, so the first thing they want us to do is write the overall equation. You can do that because all you're going to do is add it up, right? So N2O plus N2O plus O, and I dropped all the subscripts of the phases, but sometimes you can't because it goes from a liquid to a solid. But sure, you can simplify that.
Why is there an O in the notes?
Yeah, because there's 2 of those too, right? All right, what shows up on both sides?
O in O.
Right, O. So this is called an intermediate. What I crossed out in red is called an intermediate. So it showed up in an earlier step, but then was consumed or used up in a later step. So that's an intermediate. A catalyst.
Is the intermediate or like a reaction thing?
No. What I crossed out, the O, is an intermediate. So it's a molecule or a substance that shows up from an earlier step and then gets consumed in a later step. That's what an intermediate is. This particular reaction doesn't have a catalyst, but where would a catalyst show up? Where?
The fast one.
When we write it in a 1-step, we usually write the catalyst over the arrow, right? But in these mechanisms, you might see it as a reactant, and I'm just going to put A, as a reactant here, but then it would show back up as a product at a later step. So you could have a catalyst as a reactant in an earlier step, and then it'd be a product in a later step, where an intermediate is going to be a product in an earlier step and a reactant in a later step. Does that make sense? So like A would be a catalyst, and hopefully I picked one that has one in it later, but we'll see. Okay. All right, so then the overall reaction is 2N2O yields 2N2 plus O2. Agree? All right, now write the rate law for this reaction. Well, since we have a mechanism and we have steps to a mechanism, each one of those is an elementary step. So we can write the rate law just based on the slow step. So the rate is going to be K times N2O to what power? 1. You have to write it based on the slow step, not the overall reaction, right? So it's to the first. So it is a first order reaction. Okay? It's easy when the slow step is the first step. Okay, that life is easy then.
That reaction we wrote there where we crossed stuff out with the simple one, that's the elementary reaction?
No, this is the overall reaction. This is the overall reaction. These are the elementary steps to that overall reaction. The
Okay.
intermediate
O
is O, what I crossed out. Right, right. It's made one place and used up somewhere
So
else.
the catalyst doesn't get used up, is that why? Is that the difference?
Right, a catalyst could be used, but it has to come back at the end, right? Because a catalyst has to speed up a reaction by not being permanently changed. So it has to show back up later. All right, let's look at the next one.
Wait, but why is the catalyst in the slow reaction? I thought the catalyst like speeds it up.
Well, I just put it in to show you where it's gonna. Yeah, and it still could be faster than this thing happening in one step.
Alright.
I mean, it could. And that's, we're not analyzing the difference between doing this in one step and doing this in two steps. All right, here's another one. Okay, let's add this one up and find the overall rate law. Now this one's asking for somebody might have to pull up their book. I can pull it up in a second. But for a particular equation, so they're giving you the equation, which we're not seeing because it says equation 1424, produces a rate law consisted with the one from this. So let's write the rate law based on this. First of all, write the overall reaction. What gets crossed out? Okay, everything else stays, right? So we end up with 2NO plus Br2 goes to 2NOBr. That's our overall reaction. Do we agree? Okay, what we'll have to do in the end is check to make sure that that's the overall reaction that they wanted us to get. But I'll pull the book out in a second and we'll check it, unless somebody wants to go online and look. All right, so if we write the rate law based on the slow step, what are we going to get? No, you don't have to put the one. No, I'm just writing it so you see it. No, you don't have to put the one. All right, so do you right? Because that's the reactants in the slow step. Agree? All right, the problem is that right there. What is that? That is an intermediate. And because it's an intermediate and it does not show up in our overall reaction, we cannot leave it in our rate law. So we are going to have to do some math manipulation to get it out. Okay?
Make it to the zero.
Well, not make it go to the zero. We have to substitute something in for it. So we're going to look at this first reaction and notice it goes fast to equilibrium. Well, what does equilibrium mean? Equilibrium means that the rate of the forward reaction is happening at the same rate as the reverse reaction. Agree? Little bit. I mean, I know we haven't done equilibrium yet. So the rate of the forward reaction equals the rate of the reverse reaction. That's what's true at equilibrium. How would I write the rate law for the first reaction? If I were to write it, the forward reaction, not the first, the forward reaction. The rate law would be R equals NO squared. What would it be if I flipped this reaction around and wrote it that way? Huh? Yeah, just N2O2, right? Oh. Right, so this is the K for the reverse, this is the K for the forward. But they're just K's. So if you solve this for N2O2, you end up with K of the forward over K of the reverse equals NO squared. Agree? So I can basically take that and plug it into my rate law. Okay, so I've said the rate of the forward equals the rate of the reverse and wrote those two rate laws. solved for the intermediate, and now I'm plugging in whatever is on the other side of the intermediate back into my slow step rate law. So that's going to give me K times KF over KR, right? Times NO squared times VR squared. We agree? All I did was take this for NO2 and plug it in right there for N2O2.
K times KF over KR
Right,
times NO2 squared.
right.
Why do you have to do KF over KR?
You don't really, because all of these are still constants. It's still just a K. It's a different K, so you can call it K prime if you want. But it is still just a constant. It's still just a number, right? So collectively, we can call all those just K. You can call it K prime if it bothers you that I'm calling it the same K. So this is the rate law for that overall reaction, or for this mechanism. Okay, so we would have to go back into the book and look at what equation 1424 says. Let me see if I can find it quickly. It depends. It didn't tell me. See, if we were on the electronic book, we could just click. Let's see. 1424 says. All right, this is. I don't know what color to put it in so you can see it. I'll put it in black. All right, so the book says that equation 1424 is 2NO plus BR2 goes to 2NO BR, and experimentally the determined rate law was R equals K NO squared times BR2. So if they're asking if this mechanism works or could be a mechanism for this particular reaction, it has to meet two conditions. Number one, the overall reaction has to match. Does it? Yes. So that's a check off. The other thing is the mechanism's rate law. When you wrote the mechanism's rate law, it has to match the experimentally determined rate law. Does it? Yes. So this proposed mechanism is a valid mechanism for that reaction. Okay, so two criteria. The overall mechanism has to add up to the overall equation, and the rate law from the mechanism, from the slow step, has to match the experimental rate law. Then the mechanism, you can say it works.
But how did you know that you wanted to substitute the KF over KR with an NO squared for the N2O2?
Because this N2O2 is an intermediate. I cannot have intermediates in my rate law. I can only have things that show up in this overall. And because this intermediate does not show up in that overall reaction, I can't leave it in the rate law. That makes sense? All right, so let's try another one.
What were the two criteria again?
It has to, the overall reaction has to match. So from the mechanism has to match the overall that you're trying to find. And then the second criteria is that the rate law determined from the mechanism. What are you doing? Has to match. I don't know what you're doing. All right, rate law determined has to match the experimentally determined rate law. I don't know, nor do I have time to entertain it. I don't have time to entertain it either. I don't know. All right, so those are the two criteria it has to meet. Do we even want to know?
You don't write these down.
I'm playing with a little balloon.
Who did?
So it serves him right. Okay. All right, you do this one. You determine the rate law. You use this mechanism.
I'm proud of ya.
Is it not big enough? If I zoom it in, is that better? All right, see if you can write the rate law.
Do you have a reaction that's like a loop?
Do I have what?
Like a reaction like a loop, like if you instead of create an R plus S, create an R plus P. Are there any reactions that would do that?
They could, and that's where you'd see the cat. That's where the P would be the catalyst. Then, like it would show back up.
Would it just keep on going with it?
No, not generally. No.
Wait, so
But you'd run out of Q.
Yeah. First of all,
do those three add up to?
those three, right? There's
Okay,
three
so it's
steps.
Three this time.
Right, this time it's three. So step one, step two, step three. Does not matter how many steps. Alright. Right, you don't need the third one to write the rate law. Which one's going to determine the rate law? The second one, because it's the slow step. And then why are you going to have to consider the first one as well? Because T is an intermediate, so you're going to have to substitute. Right? What am I, if I cross stuff out, T's are going to cross out, right? U's are also going to cross out. Both of those are intermediates. So neither of those can show up in your final rate law. Okay? All right, but when you start to look at your rate law for the second step, you have to ignore the fact that I crossed those out. What would be the rate law for the second step? Q times T, right? The problem is the T's got to go. So up here, and really, yes, I'm trying to make you make the rate laws equal and do all those K's, but all K's are just going to turn into a new K, right? So basically, P times P, or P squared, is going to equal T. And so you're going to plug that into there. That's it. So some new K, it's going to be Q times P squared. That's it. That's it. Yeah, because your intermediate's going to be in a product, so yes.
Oh, no. Mastering camera, we're gonna have to write that and make the K different.
No, I don't think you're going to have to account for K prime. You're still going to just call it K.
What would happen with the R? In the second.
Yeah, like, why don't you have to worry about the R's or the S? Like, what happens to the...
Those are products.
Just because they're products, you just don't need them.
But the T's a reactant here. So your rate laws are only based on concentrations of reactants. So originally you write your rate law based on the slow step. So it's Q times T, right? Because that's what your reactants are to your slow step. The problem is T is an intermediate in this, and it does not show up in my overall reaction. So I have to get rid of it. My way to get rid of it, right, is to solve. You're assuming the first step goes to equilibrium, and then right, and so right.
So what do you do? I'm confused.
You technically what we're doing now, that made it look a lot simpler. What you're doing is the rate of the forward reaction here is equal to the rate of the reverse reaction. So if I look at it in the forward direction, what are the reactants? P and P. So the rate of the forward is going to be K of the forward reaction times P squared, right? And then if I look at it going this way, what are the reactants? Or what is the reactant? T. So that's the K of the reverse times the concentration of T. So if I solve that for T, you get KF over KR P squared. I'm taking that whole thing, just like algebra class, right? When you have a system of equations, when you solve for one variable, everything that's left is getting plugged into, I just lost where I was going with it. Oh, up there. R equals, this is what we had originally. So we are taking that and plugging that whole thing into where T is. So we end up with R equals K times Q times KF over KR times P squared, which we just collect all those K's and call them K. And then Q P squared.
So you don't need to worry about the products at all.
Not in your
wait.
rate laws.
So the K in how do I explain this? When it's R equals K times Q times KF over KR times P squared or whatever, they're at the bottom in the red.
Uh-huh.
The one right up from the bottom.
This one?
So that K is different than the K with the one.
Yeah.
Okay.
This is a different K. This is a different K. This is a different K. But they're all three just numbers. So
How do you find them out?
you don't need them because you're only ever going to find this one.
Okay.
I'm just showing you mathematically where it came from. But collectively, they are just K. They're just a new K. But no, the two K numbers don't match. No.
And then how do we find out K?
You'll have to have concentrations and rate to be able to solve back for K.
Oh wait, so once we find the concentration, we just do the math.
You can do, right. They'd have to give you rate and concentrations. You'd have to work your way backwards. All right, you think you got it? Sort of?
Kind of. Do you want us to write like a K1? Or can we just write
I
K?
think Master and Kim will just take K without the prime thing. I think it will just take K. We'll just generically call it K. Huh?
It'll tell you where to put like K1, K2.
Oh, it does. Okay, so it does. So he's already looking at the Master and Kim. So